Good afternoon or good morning, depending on where you are. Today, we are looking at additional lectures in thermodynamics. We want to look at entropy and other state functions. We want to look at entropy. We want to look at Helmhotz function. Entropy is designated as S. We look at Helmholtz function also, and we look at Gibbs free energy also. So let's start with entropy. Suppose we have a system, and we are doing irreversible work. Let's say we are doing irreversible work. This will be fed into the surroundings in form of heat. And remember, whether you're doing work from the surroundings into the system or the system into the surroundings, it doesn't matter. It's a question of notation. But we are saying, suppose you're doing irreversible work. Remember, we talked of reversible work and irreversible work. And we know that if you remember the indicator diagrams for reversible and irreversible work, we had the isotherm, and if we expanded the system from some volume V1 to V2, under irreversible work, the work done was that one which we have shaded there. That is W irreversible. And when it was done reversibly, a lot more work was done. So we had all this area which we had for irreversible work, including the area which we have just dotted there. So reversible work achieved more than irreversible work in terms of output. And so what are we saying in a nutshell? Remember, reversible processes, we said those are processes where infinitesimal modification of a variable reverses the direction of a process. This we discussed in our earlier lectures on pressure volume work. Now, in the case of irreversible work, it leads to degradation in the quality of energy in the surroundings. In a nutshell, there is an increase in entropy. What is entropy? S. Entropy, in layman's terms, is a measure of the extent of chaos in a system. So most systems tend to be more chaotic. And so in technical terms, we talk of dispersal of energy. So that's why we have said irreversible work leads to degradation in the quality of work, of energy. Irreversible work leads to degradation of quality of energy in the surroundings. Now, like we have said, if we have our surroundings and we have, say you are doing that irreversible work, in your surroundings, you are doing irreversible work, in your surroundings, and you have your system here. This system, let's call that system, and let's call these surroundings. Remember, system is that part of the universe in which you have special interest. Surroundings is where you make your observations. The universe is basically the system together with the surroundings. So if you're doing some work here, let's say irreversible work, being done across the worlds, what we are saying is that there will be a change in the entropy of the system, which will be given by ds of that system will be greater or equal to dq of the system, heat transfer to the system, divided by the intrinsic temperature of the system. Remember the system as a temperature. The system as a temperature. So when you do irreversible work, then the change in the entropy of the system is given by the heat which has been transferred to that system divided by the intrinsic temperature of that system. And this particular expression here is very, very important. Always remember it we call it Clausius inequality. And in general, Clausius inequality for ds is greater or equal to dq over t. Very important. And if you look, for example, at phase rule and the likes, Clausius inequality plays very important part in all that. Even if you look at the energy cycles, it plays a big part in those calculations. So that is the expression for entropy. Entropy change. Now, how does entropy relate to volume, for example? How does entropy relate to volume? That's the relation of entropy to volume. To volume. We go back to the first law of thermodynamics, where we are going to use the non-flow first law of thermodynamics. That is du. First law of thermodynamics. Du is equal to dq plus dw. Now, if we are dealing with a perfect system, that is a system obeying ideal gas equation of state, and we are assuming it is isothermal, then remember that du will be 0. And we saw this when we worked with the Joule's experiment in one of the lectures, because remember, u was a state function. So if u is a function of volume and temperature, being a state function and an exact differential, it can be written as del u, del v, dv t constant plus del u, del t, v constant dt. And from Joule's experiment, we saw that this coefficient was 0 from Joule's experiment. And this expression here is CV. That's the isochloric heat capacity. So basically, CV dt is equals to dq plus dw. Now, if the process is isothermal, then that dt will be 0. If isothermal, that dt will be 0. That is constant temperature, then that quantity there will be 0. So what becomes of our expression now that we have a perfect system and isothermal conditions? Then it means that dq is equals to minus dw. But what is dq? Remember, from Clausius inequality, we said that ds is greater or equal to dq over t. Therefore, dq is equals to t ds. So we can plug in that expression for dq into that particular equation. And we know for PV work, we are only talking of PV work, no other work. Remember, this electrical work, all manner of work are there. So when we talk of PV work, we are just talking of pressure volume work. But that is not isolated that. Because when we have work, always remember that. Take note of that. This dW can be PV work, or it can be dW, can be non-PV work. But we don't go to non-PV work. We always want to deal with the pressure volume work. But if you have to deal with non-PV work, then just get the expression for work for that particular system. If it's electrical work, you get the expression in terms of the current, time, and potential, and so forth. So now, we know that dW is minus P dV. So if we substitute all these quantities, then we have that for isothermal process, isothermal and perfect gas system, then dq, that is 0, is equals to TdS minus P dV. And we have said that the gas is perfect, so we use the ideal gas equation or equation of state. That is P is equals to nRT over V. So we plug that in there. So we have TdS minus nRT over V dV. Remember, this is P. That is P. And so, if we divide, we can divide throughout by dt. We can divide throughout by t, dividing throughout by t. We obtain the expression we now obtain the expression ds is equal to minus ds is equal to nRT, nr, because we have divided throughout by t, so that we have divided by t here, divided by t here, so these t's cancel out, so we have ds is equals to nr dv over v. And of course, using the identity, which we have now used severally in these lectures, thermodynamics, that the integral of dx over x is the same as natural log of x plus c. C is the integration constant when you have not specified the limits of the integrand. So we have ds, therefore, on integration, we have integral of ds from some quantity, some initial to some final quantity, will be nr integral of dv over v, from some initial state, some final state. And of course, those states are defined by thermodynamic functions or variables. So we have, on integration of this, we will have S, the final state, minus the entropy, the initial state, will be equal to nr natural log of v in the final state over initial state. So this is the relationship between entropy and volume of a system. Now, when we are talking about the volume of a system, it means that it is also important to know how it relates now to the temperature of a system. Once again, in this particular case, we have entropy, the change in entropy here, delta S, and we have our relationship with volume. And you have seen that we have used the first law of thermodynamics to get our quantity. Now, suppose we go back to the Clausius inequality, dq over t, and we are dealing with this system under constant pressure, Now, that means you're talking about heat being transferred under constant pressure, which you already know from other lectures is the change in enthalpy. And we said that this is a thermochemical observable, that's a thermochemical state function, and this key link between thermochemical observable and thermochemical state function is critical thermochemistry. So, we will have under constant pressure ds will be greater or equal to dqp over t, which is basically dh over, that will be dh over t. But what is dh in terms of temperature? We know that the isobaric heat capacity is dh over dt. And so if we plug in that expression there, we know that dh therefore will be cp dt. And so what is that? If you plug it into the system there, we have ds will be equal to cp dt over t. And so if you integrate between some two temperature limits, some initial to some final temperature, then the integral of ds from some initial temperature value to final temperature value will be cp dt over t from some initial temperature value to some final temperature value. Mark, note that cp. We are assuming the cp is constant. That's why we can bring it out of the integral bracket. But like we have mentioned in some other lectures, when we derive the cutoff equation, we know that cp in general is not a constant. It's having some series form, can be a plus ct squared, etc., etc. So you have to plug it in there and solve that particular integral. So it normally depends on temperature, but here we are assuming it is constant. Therefore, what are we going to have? We are going to have S as some final temperature minus some initial temperature, S as some initial temperature, is equals to Cp, again using the identity which we did, into natural log of T, some final temperature over Ti. Again, this relates the entropy to temperature. Very important. So we have seen how we can relate entropy to volume, the entropy change with volume, and the entropy change with temperature. Now, entropy, like we have already said, very important. But there are other functions, thermodynamic functions, which have the entropy element in them. Let us start by looking at the Helmhotz function. Helmhotz function, and it's denoted as A. The Helmhotz function is defined as A is equals to U minus Ts. That's the Helmholtz function, where U is simply the internal energy, T is the temperature of the system, and S is the entropy of the system. So again, if we perform mathematical operation on this Helmholtz function, the change in the Helmholtz function, we get it using product rule is simply d of Ts. And that, of course, is du minus S dt plus T ds. Minus S dt plus T ds. Remember that. And so if we are dealing with constant temperature, then that will be 0. Dealing constant temperature, that will be 0. So that dA is equals to du minus T ds. So what does that mean? But what is du? What is du? Change in internal energy. From the Clausius inequality, ds is greater or equal to dq over T, and that change in energy is under constant volume. If you keep the volume constant, then that will be the same as du over T. So if you rearrange this expression, remember the heat transfer and constant volume is du. So if you rearrange this quantity, then you'll have Tds is greater or equal to du, or du is less or equal to Tds. So if you plug this expression for du into that expression there, plug it there, then what does it tell us? It tells us that dA will be equal to, du is less or equal to Tds. So if dA, remember, was du minus Tds. So when du is less or equal to Tds, if it is equal to Tds, then dA is 0. If it is greater than Tds, then this will be positive. Remember, if du is equal to Tds, dA will be 0. If you put that there, they will be 0. If du is greater than Tds, dA will be positive. And if du is less than Tds, dA will be negative. So, if we have du as less than Tds, therefore when dA is less or equal to 0, is less than 0 or equal to 0, this process, where it's less than 0, this process will be spontaneous. So if you know the value of d and c is less than 0, then that process is spontaneous. What does that mean? If you had a reaction going from A plus B going to C, it will move perfectly. Move forward, A plus B to C. If we have equilibrium reaction, then it means that the forward and reverse reactions are almost balanced. So it's very important to note that that's a criteria for spontaneity of a reaction. And also it is important to note very important, that the change in the Helmholtz function gives the maximum work a system can do. In other words, we can relate dA, we can relate it to W max. Very important. Always know. You want to know the maximum work that a system can do, then a system of a system is related to that. Know what the change in the Helmholtz function is. Then the other function which is related to entropy, which you want to delve in, is the Gibbs free energy, which is very important. When you look at the lectures you have had, you see that the stability of phases was dependent on the chemical potentials, and what is chemical potential is the change in the Gibbs free energy. Now, Gibbs function, and it's denoted as G. And this G is related to entropy. G is equal to H minus Ts. And so, again, when you look at the change in the Gibbs free energy, then G is equal to the H minus T ds. Now, how do we bring in the relationship between dH and TdS? Exactly what we did with the internal energy. We know heat transfer and constant volume is du. Heat transfer and constant pressure is dH. Therefore, going back to the Clausius inequality, we have that ds is greater or equal to dq over t. So under constant pressure, that is dH over t. Therefore, t ds is greater or equal to dH. Or we say dH is less or equal to t ds. Once again, if you put this relationship here back into this one here, if you put it there, then it tells us that ds, where are we? We are that dg, if dh is equal to tds, dg will be 0, which we said was dh minus tds. We said that if dh is equal to tds, dg will be 0. That's an equilibrium reaction. So when you see dg, delta G is 0, there's no change in the Gibbs free energy, that's an equilibrium reaction. This G is written like a Q there. That's dg is 0. Of course, if you integrate to get delta G is equal to 0. Now, we are also saying if dH is less than TdS, if it is less than TdS, then dg will be negative. And that's a spontaneous reaction. That is, when dg is less than 0, that's a spontaneous reaction. And that's the reaction we want. When you are having a reaction, you are having some reactants, you want them to go to products. You want the delta G value to be negative. That means that reaction will proceed in the manner you want it. The reactants going to form products. If it is 0, that's an equilibrium reaction. And of course, if it is positive, then that will be a non-spontaneous reaction. So if the H is greater or equal to TdS, is greater than TdS, then dg will be positive, and that's a non-spontaneous reaction. So, these are very important state functions. Entropy, Helmholtz function, Gibbs free energy, they are spontaneous. They are state functions, and they're exact differentials. Very, very important to note that. They are state functions, and they are exact differentials. And number two, that means they don't depend on the path, they only depend on the initial and final states of the system. Depends on the initial and final states of the system. And we have seen that using the Helmholtz function and the Gibbs free energy, we are able to tell in terms of the spontaneity of a reaction. Let's stop at that particular point. We'll pick up with other thermodynamic lectures.